Okay, so this is the first lecture for Earth and Space Science. You're not going to have very many videos for this class because I prefer to do my lectures for Earth and Space in front of everybody, especially when we're doing the space part because, well, it's just more fun to talk about as a group. But for this particular lecture, I figured that you would get more out of it if you could just do this part at home and then the assignment we could work on in class. So the first thing we're going to look at is system, and we're going to be looking at a lot of systems in Earth and space this year. The solar system, the rock cycle, the water cycle, weather systems, and systems are parts that are interrelated that form a complex whole. One system is the water cycle. It has its own parameters, meaning that it has different events that happen, such as condensation, precipitation, evaporation, but it does not function independently. Okay, and so because of that, it's called a system. So in this class, we're going to be looking at lots of systems. The first being basically the solar system and how the universe was evolved or created. The overall goal of science is to discover the underlying patterns in the natural world, then use this knowledge to predict what will or will not happen given facts or circumstances. So we're going to be looking at lots of real world examples, and that's one reason I really like Earth and Space Science, because this is one class that you can never ask me, what does this have to do with the real world? Okay, we're talking about the universe, the planets, planet Earth, rocks, weather, climate, oceans. All that has to do with the real world. It is the real world, and it has to do with real life. And so all parts of this course affect what happens to you. So when you're doing research, scientists use two methodologies in order to do that research, qualitative and quantitative. And in the qualitative research, you're going to be looking at details, descriptions. So, words, basically descriptions of what's going on. So, if I could say the rocks are, you know, round or jagged, their colors, what kind of streak they leave on a mineral plate, which we'll talk about, and so forth. So, they're descriptive words. Quantitative research is research that you will use data, will use numbers or quantities. And we'll talk about independent and dependent in just a second. But if I go back for just a second, that first bullet, why Earth science, one reason why Earth science is so unique is because the systems that scientists study in this particular branch of science could be very large in scale, especially when you're talking about the universe or the solar system, or even the water cycle that's covering, a huge area or over long periods of time. And so, especially when we get to historical geology, you'll see that it takes millions of years for some of these layers of rock to form. And you'll see that when we look at a cross section of the Grand Canyon. And so sometimes earth science is a little harder for people to understand because it's beyond our normal understanding of time. Fact versus opinion. That's also something that you need to know. A skill in science is knowing the difference between observation and inferences. Let me start with observations. Observations are facts. So you see here, it is 85 degrees at 11:34 a.m. Okay, facts. Usually will have, doesn't have to have numbers, but a lot of times it's going to. An inference is basically an opinion, a generalized statement. So you could say it's warm outside instead of saying it's 85 degrees. So fact versus opinion, observation versus inference. Know the difference. Okay, when you're doing an experiment and you're gathering your data, you need to know what it is that you're changing in an experiment. So the first thing is your independent variable. These things, these four bullets right here are really important because a lot of students will mix them up, especially the independent and dependent variables. So you need to be well versed in those. So the independent variable is the one part of the experiment that you change or manipulate in order to observe what happens. On a graph, the independent variable is placed on the x-axis. So time is generally a, excuse me, time is generally placed on the x-axis. A dependent variable, that is the thing in the experiment that changes because of the change in the independent variable. So let me come up with an example of an experiment. Say you have three plants and you are going to feed them three different liquid substances: water, salt water, and cola. What is the independent variable? It is the substance that you fed them. Now, there are several things that the dependent variable could be, but usually it would be something like growth. So the growth or the height of the plant depends on the substance you feed it. Okay? Constants are all the other variables in the experiment that must stay the same, because you can only change one thing in an experiment because you're trying to observe uh, the response changes. So in our plant example, the temperature of the room, the amount of light they're getting, the amount of the substance they're being fed, the location, the type of plant, all those things have to remain the same. The control, and I should have put the words on here, is basically a standard of comparison. It is the norm. What would be expected to be the result, or what would normally be used? So in our plant example, what would the control be? Water, because we normally feed a plant water. Okay. After experiments are done, and we'll talk about the scientific method, so I guess these are a little bit out of order, so I apologize for that. But you know that one of the steps of the scientific method is to form a hypothesis, which is your educated guess about what's going to happen. If that educated guess has been tested repeatedly and has lots of support, lots of evidence to support that hypothesis, it can become a theory. So, for example, the Big Bang Theory, the theory of relativity, the theory of plate tectonics, the theory of evolution. These things have been tested and evaluated many, many times, but are not proven to be absolutely true. It is not absolute fact. When something has been proven without a doubt to be true, in which there's no known deviation, then it's elevated to law. So the Newton's laws of gravity, the laws of thermodynamics, okay, at least on Earth, those things do not change. They have been proven basically irrefutable. In an experiment, sometimes you'll make a model, and you probably did that in middle school. You've probably done that in high school already. It's when you make a representation of something that's too big or too small to view it in its entirety. So later on in this course, you'll be making a planet, a styrofoam model of a planet to hang in their room as part of our solar system, because that's too large to view, or a model of a piece of DNA, or an atomic model, because those are so small they need to be blown up to see. So now we get to the scientific method. Once you're done with this video, or you can even pause right now and open a new window and go to the video, and I'll tell you how to do that. Well, I can tell you how to do that now. If you go to YouTube, I have a channel called S. Sahabi. On that channel, you'll find the scientific method. This would be a good time if you want to pause this video and go on to that video. It's about 4 minutes long, explaining the scientific method, so you don't have to sit through me talking about it in class, and then you can come back to this one. When you're doing the scientific method, there can be several hypotheses for the same observation. For the purposes of our class, when you're designing your experiment, you're going to want to only come up with one hypothesis that you want to prove or disprove. Once you have either accepted or rejected that hypothesis, then you can move forward. If your hypothesis was rejected, but you really want to find a hypothesis that works, then you can start over again on your experiment and come up with a new hypothesis. Ultimately, it needs to be testable, replicable, meaning you have to be able to do this experiment over and over again. It should be able to be proven false. And then, if you were a legit scientist, it would be peer reviewed by the scientific community, and then it could be elevated to a theory. Here are the steps of the scientific method. Notice the arrows. Okay, so sometimes you have to, rearrange your steps a little bit and retest, especially if the hypothesis was not met. There's no one right way to do the scientific method, but you need to at least have your hypothesis, your objective, record your observations and your measurements, and try to explain what's going on. Okay, and then, like I said earlier, your hypothesis is either rejected or elevated to the status of a theory or a law. Now we come to the collecting data part. In your experiment, basically what you're going to do later on is you're going to look at this set of materials that you're given, and you're going to try and design an experiment. So it's completely up to your group to decide what it is you're trying to find. Every group will need to be collecting data. So it has to be some kind of an experiment that is measurable. So when you collect data, you need to be precise in your measurements. So you would need to use a stopwatch if you're doing something with time. 4 seconds sometimes isn't really precise enough. Maybe you really need 4.3 seconds or 4.32 seconds. If you were dealing with someone running, you would need more precise times. Measurements that have a number and a unit, that is something that I am very, very particular about, are units. So many times in experiments, the students will write down their measurements, excuse me, give me the numbers, and then fail to put the units. Well, if you're dealing with several groups of data, I don't necessarily know what you're talking about if you don't use a unit. So please make sure you have your units and that they are in the SI system or the metric system. I am okay, however, if you do something with temperature, you use Fahrenheit. That is okay. Although I believe most of our thermometers use Celsius anyway. You need to keep in mind again about what measurements you're taking using the correct units. Significant digits are not going to be as important in this class, but they probably would be important in other science courses. Scientific notation you will have to practice and know, especially when we're talking about great deals of time or distance, especially when we're in the astronomy unit, and be able to convert from one unit to another. That's dimensional analysis. I know you did that in chemistry when you had to go between kilometers and miles. A lot of times, though, in this class, that might be the only one you have to do is kilometers to miles. Otherwise, you know how to put hours into seconds and etc. All right, this last part I'm going to go through kind of quickly because you've been doing graphs since you were in elementary school. But graphs are important. Graphs and data tables are important, and it's important especially to know what kind of graph to use. And that's another skill that some students, haven't really mastered yet. They have this data, they wrote it down, and they say, well, Miss Sahabi, what kind of graph is this? Well, you just have to look at the information. If you're talking about what are the parts of a whole, what percentage of something that they're doing, well, then they're going to use a circle graph. I'll go back to that one. The other type of graph would be a bar graph. That's when you are comparing values. So if I want to say, as in this example says, the frequencies of tornadoes in individual states. So I could be comparing how many tornadoes in Mississippi, let's say 4, versus 32 in Kansas, I can put that information in a bar graph and I can very easily compare the values. Lastly is a line graph, and that's going to be quite common, especially when dealing with time. If you're doing something that happened over time, usually that's a line graph. Not always, though. But let me go back for a second. So, you're used to seeing graphs. They're in textbooks, they're in newspaper articles, magazine articles, online articles, and so forth. It will be used heavily in college, so it's really important that you realize and recognize the different types of graphs. And I'm really hoping that you'll be able to figure out which kind of graph to use in your own experiment before you ask me. So here are the rules for basic graphing. I'm not going to read this to you, but basically, these are the things that you need to make sure you do. Label your axes. Make sure you understand which one goes on the x. X is the independent variable. That's the one that you changed. Y axis is the dependent variable. What changed because of what you changed. So in the plant example, the type of substance would go on the x-axis. Okay, let's say we're measuring height. Okay, and so, the height after 5 days. So the substance, water, salt water, and Coke, would be on the x-axis since that's what we changed, and the total amount of height, probably in centimeters, would be on the y-axis since height is what changed. So making sure that your axes are labeled with units, okay, is important. Also a scale, and to use that scale to stretch the length of your graph paper. The scale you need to choose needs to be readable and regularly spaced. So 2, 4, 6, 8, 5, 10, 15, 20. You don't want to have something that goes, 1, 2, 5, 6, 7, 8, 9, 12, 14, 16, etc. Okay? You don't have to start at 0. If none of your measurements start until the number 20, well then start on 20. So again, axes being labeled, a a title is extremely important. And if you're doing a line graph, a best fit line would work. Okay, so that is the end of your first lecture in Earth and Space. I hope my voice wasn't too monotone because this is my first time. So if you haven't already, this is the time where you want to go to my channel on YouTube and watch the scientific method video. That needs to be done by tomorrow. Thanks.